And with this demo, I'm also hoping to demonstrate some of the things you should do while you are taking the assessment. And I'll also talk about some of the things that you will get from the system that you should ignore. Which I guess for the question type I'm attempting isn't affected, but some of the other question types it might be affected. I'll explain why after the attempt. So let me get started with electrostatics freeform timed assessment. Again, I know what question I'm getting because I spent some time loading the dice for test student. So, and I'm gonna watch the time because I only have 20 minutes. Two infinite conducting plates arranged parallel to each other, separated by distance d, are connected to a battery. Okay, battery provides a voltage difference V. Okay, so let me do this. I'm gonna just paste this into the OneNote so that I can draw on top of this. Oops. Yeah, I think that's gonna be fine. Yeah. All right. Linked together. Oh, that could be good. Let's see if they are. Yeah. So describe briefly how following drawing should appear. Electric field lines should look something like this from the... Does it describe upper plate at higher voltage? So plus V here, and I guess 0 volt here. Then electric field lines should look like this, and they should be equally spaced for uniform electric field from one plate to the other. So that's my electric field. And then equipotential surfaces, let me do it in different color with the dotted lines. They should look kind of horizontal. The main feature I'll be looking for is that they are perpendicular to the electric field. And the other, I guess, second main feature is that they should be equally spaced between each other. It's again tied to the fact that the electric field is uniform in this setup. So that's as best as I can draw freehand. So I'll be attaching this into attached work, but in the answer you should give a word description, like you are describing this to a blind classmate. So electric field vectors should be directed vertically from the plus V plate top to the lower 0 volt plate at bottom. The field lines should be evenly spaced throughout uniform electric field. The equipotential lines should be directed horizontally, perpendicular to the electric field lines wherever they cross, and the equipotential lines should also be evenly spaced, uniform electric field. Yeah, so that's the drawing. In our old midterm exam, I would have people actually just draw on the exam, but this is best I can get it to work in the online setting. So infinite plate. It can be proven that electric field between the two plates are uniform, has magnitude V naught over D. It can also be proven that the electric field outside the region between the two plates is exactly 0. Summarize the key points needed for the proof in the space below. You can also include you can, don't have to. So key point. We start with the sense of the electric field directions. We drew for A above. Without explicitly saying that E field is 0 outside of the plate. So I might say for the drawing, let me say, including B, there could be electric field outside, you know. I think I don't have to necessarily say that electric field outside is 0. Um, outside of the plate, from the translational symmetry, translational rotational around the axis perpendicular to the plate, and mirror, like flipping right and left, mirror symmetry of the setup. We know that E field can only be perpendicular to the plate, and the E field can only depend on the G coordinate, G axis being the axis perpendicular to the plate. If you move horizontally, that shouldn't change the E field. That comes from the translational symmetry of the setup. Exploiting this symmetry, we can use a pillbox type Gaussian surface to show that electric field between the plates don't depend on the G coordinate either. Move the portion of a pillbox surface between the plates up or down. So I'm describing a Gaussian surface that kind of looks like this. So yes, just to show some perspective view. So this will enclose some charge. So that enclosed charge is what gives you the net flux, and you argued, that the electric field is uniform, so E dot A is constant and all that. So what you are then doing in this argument is imagining moving this surface up or down. And as you do, the flux doesn't change, which means electric field through this surface must not be changing. Either move the portion of the pillbox surface with the plates up or down. Net flux doesn't change, which also means the electric field doesn't change. Gaussian surface to show. And now how would you prove proving the outside fields must be 0 is, I think that's a trick here, because if you do surface like this, then I think challenge is that with the field directions, you could have non-zero field but zero flux. Zero flux that's mandated by the amount of charge you are enclosing. So I'll say following the outcome must be 0 is trickier, but we can do it by doing the derivation of E field due to a single infinite plate. E is equal to sigma over 2 epsilon naught. That's a formula you can prove, and using superposition principle, because E field of infinite plate doesn't depend on G coordinate. The fields outside the plate exactly cancel. Yeah. So that's enough of a detail, and because I'm going to exploit the fact that question didn't ask for actual proof, it just said summarize the key points. So I did that, and by saying Gaussian surface, I'm implying that I'm using Gauss's law. I think that's enough. Maybe not the model answer, but it's one I'm giving within the time limit. All right. Calculate the pressure, force per area on the top plate due to the bottom plate through their electrostatic attraction. Oh, okay. So for CA, I guess what I have to be careful is that I don't include the field due to the top plate. So really what I have is the bottom plate will have negative charge on it. So it'll be producing electric field that looks like this on its own. Let me just finish with this one. It's going to be too many. And the expression for that electric field will be the amount of charge, which I don't know. But actually, sorry, I didn't fully complete B, I think. Uniform and has magnitude V over D. So let me finish that. The E field, the fact that the E field is V naught over D can be shown from the definition of voltage, which is that V delta V is equal to E times delta X. So here V naught minus 0 is equal to E times D. So E is equal to V naught over D. The effect, so this would be actually E average. Fact that E is uniform between the fields, I mean we can replace E average with E. Yeah, and I'll be making use of the fact while I'm doing part C. So here E would be sigma over 2 epsilon naught, and comparing that to the electric field that should be here, which is the sigma over epsilon naught, which is equal to V naught over D. I can re-express this in terms of quantities I have, which is half of that electric field, V naught over 2D. So that's the value of the electric field here. So for the top plate, which is here, the distance doesn't really end up mattering anymore. So if you imagine a little surface area element, the amount of force being pushed this way, the force would be the electric field times a small amount of charge dq. So you can express that the small amount of force on that is equal to electric field V naught over 2D times the small amount of charge dq. That's going to be the surface charge density times the area, dA. So it mentioned the pressure. If I have dF divided by dA, this will be the pressure. So all I have remaining is making sure that expression here is in terms of the things I have. I have V naught D, that's fine. Sigma is something that I don't have, but I can use this expression to express sigma in terms of things I know. So sigma is equal to epsilon naught V naught over D. So plugging that in, I have the amount of pressure is equal to V naught times V naught and D times D in the denominator. So it'll be epsilon naught times V naught squared over 2D squared. And just because I'm supposed to be trying to use the Coulomb constant more, I just have all the formulas memorized in terms of epsilon naught. But the substitution I'm using is the fact that Coulomb constant is equal to 1 over 4 pi epsilon naught. Or alternatively, epsilon naught is equal to 1 over 4 pi Coulomb constant. So I can replace that and say pressure is also equal to V naught squared over 4 pi times Coulomb constant times 2. So that 4 is actually 8 now. So that 4 is 8 pi k epsilon ke times d squared. So this is these both are valid expressions for pressure. So yeah, magnitude pressure is so here. So I'm gonna get automatically graded. Somehow I didn't see that when I was looking at this question. So so I'll get automatic grade, and I will talk about what that means, what it doesn't mean, after I enter this. Pi KE. Using this, one thing it helps you with is it helps you make sure that you don't use any variables that you shouldn't be using. So, all right, that's the magnitude of pressure, and this is the same answer you would get if you simply average the electric field inside, outside, and use the average value as the electric field on the plate. It just works that way. Let me not get into a rabbit hole that I don't have time for. If you release an electron in the middle, so like at d/2. From rest, what is the speed of the electron, the moment before it strikes one of the two plates? Okay, so I think for what I'm gonna use is conservation of energy. So this is actually physics 4A question. So just quick sketch. I'm releasing electron from here. It's gonna go strike the positive plate and be here at the end. So let me call this a snapshot 1. Call this snapshot 2. So if I have a sense energy is conserved from snapshots 1 to 2. So I'm gonna say my total energy in snapshot 1 is equal to the total energy in snapshot 2. Total energy in snapshot 1, just the potential energy. So here my voltage will be V naught over 2. Here my voltage will be V naught. So potential energy is minus E charge times V naught over 2 plus the kinetic energy is 0 at this snapshot because it's released from rest. In this snapshot, my potential energy is the charge times the voltage, and the difference will end up being E V naught over 2 plus the kinetic energy, 1/2 mv squared. I'm being asked for speed, right? Yeah. So it's a matter of just solving for this lowercase v for speed. So in the interest of time, I'm gonna do the algebra in my head. V is equal to the 1/2s cancel out, square root of E V naught over m E. I think that's it. We'll look up the answer, see if I got it wrong later. So square root of E for the elementary charge times V naught divided by ME. And by the way, my open method understands implied multiplication, so if you didn't have this, it'll understand it fine. So I think that's it. So assuming I did everything correctly, when I get the score, I should get score of 50%. That's coming from these two that I hopefully answered correctly, and the rest. And these two are automatically given a score of 0, which is the part that I'm telling you should ignore, because all the manually scored parts, they just want you won't have any proper scores for that, because they are manually graded, and I'm not manually looking at this in real time or possibly ever. I'll talk about that in class. So I think I have 2 minutes. That might be enough time to add work. So yeah, let me add work. Now for adding work, this is what I recommend for you. For you, I recommend that you take some time to organize your work, or possibly even review it to see if you made any mistakes. So that is what I would recommend for you. For me, in the interest of time, I'm just gonna copy and paste this. I think this is enough for A and B. Yeah, the other figures, they were actually for C. So for C, I'll just include the whole thing. Let's see the entire set of figures here, and then I'll have to include this portion. And again, for you, I recommend that you organize so that you don't have to attach such difficult to decipher a jumble like I am right now. Did I mention test student is my worst student? He does things that I tell other people not to do. So with that, those are my Work, again, I recommend that you take some time to organize it. When we are doing the required one-on-one meeting, you will be able to see your own work, so why not, make it prettier. I'm gonna submit it. End. Now when you do that, it won't actually end everything. It'll make it so that you can't edit these anymore. They are done. So either I got 50% or I missed something. um, but your work you can still change. In this screen you still can. And I guess let me just save a work and continue. Now, after you get past that point, you can actually still, yeah, so I got those auto graded portions correct. The other 50%, it's manually graded. So if you want to modify your work at this point, what you can do is you can refresh this screen and going through the add work button. Then you will get to a screen where you can still change the work if you feel like you need to change anything. If you go in through the review work in Gradable, that screen will not let you change anything. Not the answers, not the attached work. It just doesn't let you do any of that. Let you rotate the images for viewing convenience. So yeah, that's it. That's this one additional question that you don't have in the notes on the timed assessment page, and hopefully this is helpful to people looking at it.